So, thanks for coming today. I know you could have gone to the beach or to the swimming pool, and it looks very tempting on a day like today, but I hope to make this evening worth your while, which is an English way of saying I hope you get something out of it. It's been a few weeks, but when we last saw each other, we talked about one of the two big energy consumers, right? We talked about commercial buildings, large buildings, right? And so what we looked at was the opportunity for those massively large buildings, like this very building we're in, to provide grid services. Do you remember what grid services we were looking at or we were thinking about? Any recollection?
Yeah, but they're doing on the
It's okay. It's okay. I just keep you awake tonight, right? I know you've had a long day, but that's I typically try to keep people awake. So what we talked about was buildings participating in a day-ahead energy market, right? So can I participate proactively in a day-ahead energy market? And the other, it's a little loud. Okay, it's just right for you? Okay. And the other market was frequency regulation. So the introduction took a little long, so that's why I somewhat ran out of time this time. But I hope you get the idea that if you can put together, we talked about office buildings and large retail buildings, and if you put them together in portfolios, those portfolios may actually provide grid services that help alleviate grid stress. Okay. So, what was, for anyone who was there, what was the fundamental assumption underlying that work? When you think about it as being a control problem. Let me ask you, was it a centralistic perspective or was it a distributed perspective? Okay, other votes. Was it distributed or centralistic? Did I assume someone to put together, aggregate all these building features? I think so, right? We had that superpower, that super brain that said, you do this and you do that, and that's the aggregation part. Now today, I'll offer a very different perspective. And there's several changes. I hope I won't step over your feet I'm talking about outside. There's several things that are going to be different today. First of all, I'm going to talk about residential buildings. And I'm going to talk about residential buildings in a context where there's a need for air conditioning. And I think today's a perfect day to illustrate that, right? Today and the next few days after it will be quite warm. So we'll look at residential buildings. We will look at the cooling period, which is for the United States, different from France, but the cooling period is the time of grid stress. In France, it's electric heating in the winter, but in the United States, it's really the hot summer. And the other large departure from the last talk I gave is that I'm going to offer to you a very distributed perspective. Okay, so this is why the title of today has 3 lines. It's assessing the impact of large-scale distributed residential HVAC control optimization on electric grid operation and renewable energy integration. This work has been diligently pursued by my former PhD student, Dr. Charles Corbin, over the last 5 years, and he is now at the Pacific Northwest Laboratory in Washington. Okay, so what's the situation we're looking at? So the situation is we have our transmission system that you all know very well up there, and then down here at some of the bigger loads,
we have our homes. Some may be equipped with PV, and some may even have electric vehicles. And so the question is, what can we do in these homes in the presence of distributed rooftop solar and maybe even some grid-scale wind power to improve grid operations? Okay, and the underlying background that motivates this is as follows. Okay, so we have about 20 terawatt hours a year of increase in residential cooling every year. And I think you're all comfortable with kilowatt, megawatt, terawatt hour. That's a lot just for homes to be cooled, right? And this involves, from an initial penetration rate of 57% 30, 40 years ago to about 87%. Even my home in Colorado, which today does not need any cooling, it needs drying. It's a joke. Even my house has cooling. It doesn't really need it, but somehow it's like you buy a car, you get an ashtray in the car, right? They put air conditioners into buildings, and in many cases, I don't think it's necessary in the climate that I live in, particularly not. But what is interesting is that we are expecting an increase in total electricity use in the residential sector for the next 25 years. And it's an increase of 24% over today. So that's a very large increase. And this increase is equivalent to about 48 gigawatts, which is a number that some of you might actually have a reference to. Anyone have want to guess what 40, 50 gigawatts is equivalent to? Yeah, that's the very peak load you're saying, right? So this is just the addition, right? This is just what we have to add to keep the growing U.S. population cool and happy. Okay. So I hope this presents an interesting background. The other one is the well-known duck curve by now that you might recall. We have this animal here that today doesn't quite look like a duck, but it will, right? And what we have here is nighttime load in California. That's a California independent system operator. And with current rooftop PV, we're here. Actually, in this year, we're down here. This has been the last few years. You can see the dynamics, right? This has been 2 or 3 years ago, and in 2015, we're here. So this is the reduction in new peak demand just through the addition of distributed rooftop solar in California. And you can see where this is going, right? So the idea is we are going to see significantly more morning ramping and afternoon ramping to accommodate that rooftop generation. So the hypotheses, and I always ask my students to think about the hypothesis before they do research. And so the guiding hypothesis is it possible for, and I'll explain all the terms in a second, model predictive control in residential HVAC systems to eliminate traditional demand response? You might not know today what demand response is, but you will in a few minutes. So can I use MPC to eliminate DR? And we'll answer that question today. Can we use predictive control to provide help in generating a graceful response under grid stress, right? A graceful response is preferred over turning things off under blackout or brownout conditions. And is it even possible that this distributed MPC idea allows me to enter or to add more renewable power onto the grid? And that's basically the idea here. Can I use buildings to help me add more renewables with less curtailment onto the electric grid so that I can get higher capacity factors out of my wind and solar systems, right? Because if you put if you invest as a society in renewable energy systems, of course, you want the highest number of full load hours you can imagine, right? And so the question is, can buildings help in this endeavor? Okay, the research questions behind this work is, how should we do this distributed model predictive control? Could we do this in the real world? What kind of driving functions should we be sending to individual homes? And can we actually use it as a day-ahead planning resource, kind of a unit commitment and dispatch system? And would we possibly achieve higher penetrations of renewables? So these are the research questions that motivated the research. So how do we do this? The fundamental idea is to combine, to combine models of buildings, and in parentheses it says thousands. It is literally thousands of building models that are combined in real time with a distribution feeder model and the power flow simulation in that distribution feeder. So it's an integrated assessment in real time, an integrated assessment of the distribution feeder and the loads are considered to be flexible, right? So that's the idea. The power flow simulation is done in GREGOR. It's a Pacific Northwest Laboratories power flow simulation tool that you can, anyone can download and use. And we're using what we call, and I'll later explain, directed MPC. It's distributed but directed. So why don't I explain it now? So many things happening later. So distributed and directed means each home gets a charge, an assignment, and it's trying to fulfill the assignment as good as it can. But this institution that sends out assignment doesn't try to orchestrate at the very same time all of the participants. So it's like telling 1,000 homes, go out and do your best to achieve a certain goal, and then tell me what you've done. And then look at the total impact at the feeder level. Right? So this is the idea of directed but distributed but directed. So we're going to look at some demand reduction and load shaping performance. We're going to look at high areas of, or areas of high rooftop solar penetration, and we're also going to look at the question of wind. All this will be forthcoming. So I mentioned to you, let me make a connection to the last talk I gave. When we last talked, I said we have to develop reduced order models in this portfolio optimization. The reason was we had to optimize maybe 5 or 10 commercial building mathematical representation at the same time. Here, we have to do this with thousands, right? Because we actually have thousands of homes connected to distribution here in actuality. So the building models have to be very fast, but they have to be good, right? So the building models have they have the typical single zone representation with walls and windows and the sun rising in the east and marching across the sky and the infiltration driving hot air into the building, all these effects, people coming and leaving. Being turned on and off, and pool pumps and microwave ovens and TVs and all the things that generate heat or that provide heat losses and heat gains, all these have to be considered. And the HVAC system is what we refer to as a DX system, a direct expansion system, which is pretty similar to what you would find in Spain in many cases. In Spain, we have so-called split coil systems where you have a condenser outside and an evaporator inside, and the refrigerant is being looped back and forth. In US, cooling is typically accomplished by a direct expansion coil in a central air distribution system, and you have warm air basically being returned from the house, not hot but warm, cooled and dehumidified, and that's then distributed through the house. And we can also assume that to be a heat pump system, then the same system could provide heating. But we also add a gas furnace. Does anyone know what the difference between a furnace and a boiler is? Maybe a building term. It's a gas furnace. So a furnace makes hot air, whereas a boiler makes hot water. Okay, that's the difference. And why is this a furnace? Was this a mistake? Don't we distribute hot water through the building? For heating purposes. When we heat in the winter, don't we heat? I mean, the homes here in Spain that have heating, not every home has heating, I don't know. But the ones that do, how do we heat them? Right, but what do we distribute throughout the house? water, right? So it's not a furnace, right? It's a boiler, right? It's a gas boiler. But in the US, we actually use furnaces because for some historic reasons, the way we provide comfort in homes in the United States is air-based. It's central air distribution system. And there's actually a reason for that. And the reason is that in many climates in the United States, you do need to provide cooling in the summer and heating in the winter. I remember 9 years of my life I spent in Omaha, Nebraska, which is a curious place, interesting, in the middle of the Midwest. And I remember how, until April, I was heating constantly, and then there was a 2-week period where I could turn it off, and as of May, I could start cooling because it's one of those climates where during the winter we get all the cold winds from Canada falling into the Midwest, and in the summer we have the Gulf of Mexico, a big pot of hot, warm air coming up, right? And it's like a matter of 2 weeks. So in most, this may be an extreme case, but Chicago is the same. Has anyone been to Chicago in an unpleasant time of the year? Yes? No? Yes? Okay, you have, which kind of the cold or warm? It's crazy. Yeah. Yeah, and think of homes, I didn't have an appreciation of summers and time here in Spain until I lived here for a year, but the extremes are quite surprising. So you could provide a water-based heating system and then an air-based cooling system, but that needs 2 systems, and that's expensive. So for that reason, people use a so-called all-air system, central air conditioning system, that uses air, warm air for heating and cold air for cooling. That's why we have a gas furnace. Okay, so the refrigeration system has a compressor turning on and off, and we have a thermostat with a set point and hysteresis. And also, in the model, we have to consider what we call minimum cycle time. When you turn a compressor on, and then you turn it off again, you cannot turn it back on right away. You have to wait a little bit for the gas to settle, for the refrigerant to settle. And that's minimum cycle time. So how does this look? So this is, I showed you lots of pictures and few equations, so that I can tell you today. So this is temperature, and this is demand. And this is the outside temperature in, I believe it was Houston for this model. Doesn't really matter. Something where it gets 36 degrees. This is like today, right? This would be exactly like today. The difficulty was it started out to be pretty warm already, right? 24 is the minimum temperature outside. So what happens in the house, you see the set point being at about 23, 22 point something, and then it's being set up and then being set back. Anyone have an idea what's happening here? Why this? It's very common.
Many people is not in the house.
Exactly. People are in the house, and then they leave, and then while they're gone, they feel like, oh, I should save a little bit of energy by raising my set point, right? But you can see what happens. This is just to show you the compressor's cycling, right? And you can see long periods of duty cycles, and you can actually see the compressor power turning on and off. And then as it gets hotter, you can see this long period of operation. This compressor stage 1 was running continuously, and then as the set point was raised, what happens? Well, the compressor turns off for a few minutes, 10, 15 minutes, but then comes back on. And it's still getting hotter, and that first stage is not enough, so the second stage has to come on. You see that? Cycling on and off. And then there is a period in the afternoon around 6 p.m. where we have both stages running continuously. What would that be? What happened there? It's 6 p.m. It's no longer the hottest time of the day. It's only 32. Exactly. So the set point is being reduced, and so I'm actually asking my system to work very hard at that point of the day. I'm going to stick with this for now. Okay, so you can see superimposed here a few electrical loads that we assume in this house. Okay, so this is how we have each of the houses being modeled. Now, I'll talk about more of the homes in a little bit. We compared our simplified model against Energy Plus and some other big heavy guns, as we would say. Not really heavy guns, but you get the idea. A very big, accurate system in a context which we refer to as best test, which is a standardized set of tests. And you can see that the results are fairly simple. These are the differences in cooling related to kilowatt hours, and so they're relatively small except for this this last case back here. So we feel this is a validated model. That's the idea. And so these are the cooling load profiles for June and July between a full-fledged Energy Plus model and the reduced order model. And RC is resistance capacitance in this case, and there's a deviation of 5.5%, so it's pretty good. So on the grid model side, we're going to look at 3 different distribution feeders, and we're modeling all components of the system from transformer to lines to lights. And GridLab D solves the unbalanced power flow for this 3-phase distribution system. And we're given 24 representative feeder models, and we're picking 3 of those. And the 3 we're picking are those 3, Houston, Los Angeles, and New York. And those are studied because they do have a significant cooling load. And let's just look at Houston for right now. This is a 22.9 kV feeder with 12 megawatts of nominal load, 14 transformers connected to it, 284 residential transformers, and that serves a total of 2,146 homes. And 80% of those have, 80% of that load is residential. So 80% of the total consumption on the feeder is 2 buildings, and 98% of the homes have air conditioning in Houston. Right? Who's ever been in Houston knows that's a necessity. What's different in Los Angeles? Giving me an opportunity to drink of it. It's near the sea, yeah.
Sea makes the warm temperature in winter and summer.
Mm-hmm.
So, by that, it doesn't need any air conditioner.
You less so. I wouldn't say you don't need any, but you can see only half of the homes have air conditioning, right? But still 78%. You get an idea that even in mild Los Angeles can get warm. There's a city, San Francisco, that is year-round the same 20 degrees. No one has air conditioning. There's one city where it's always the same climate, the Bay Area and San Francisco.
In summer, it's horrible.
Okay, it's horrible. Yeah.
The humidity is very high, and I think it's 30 degrees.
Yeah, it's so you're not surprised, Antonio, that 79% of people have
Very well known blackout, huge blackout in the 70s because of these
situations. Okay, so these are my 3 prototypical feeders I'm going to look at, and just for you to understand, when I'm talking about distributed but directed model predictive control, it actually means I'm going to tell a significant fraction of 2,146 homes to optimize their building operation. Okay, so that in the case of Los Angeles, only 1,300, but nonetheless. Okay, so the electric loads are modeled as so-called zip load, constant impedance, constant current, and constant power loads, and those fractions are then used to produce power and react to power. And we generated those from the GridLab D model, and the analysis showed that to be an acceptable simplification. Okay, so now we take the Houston, New York, and Los Angeles feeder models, and we compare the original GridLab D with our new system, which we call Grid MPC. Why do we need a new system? Because we want to optimize, right? We want to do something with the building. Because GridLab D assumes the loads to be static, not flexible. And I hope that what you see is that there are differences, and the differences we track back to differences in how solar radiation is considered. But for for Houston, Los Angeles, and New York, you can see the agreement between the original grid lab system and the new grid MPC. And MPC is model grid control. The agreement is, as you can see, is pretty high. And another thing you can see here, Los Angeles is characterized by basically no annual or annual profile. It's pretty much constant climate throughout, which is why so many people live in Southern California, because they like it warm. Okay, good. Let me skip that. So the MPC framework, how do we do that? It ended up being a Java-based framework that integrates all these possibly many thousands of reduced order models of residential homes. And it included the model predictive controllers and the power flow simulation. The weather is energy plus weather files, so we can use any weather file we want to, or typical meteorological year. And the buildings, as they go through time, they have states, and the states are persistent. So if I pre-cool or heat or do something with my building, the next time step, the next optimization remembers the states. Okay? It's important, so we have dynamic treatment of all these buildings. Now, just to save this for a minute, the optimization of about 1,500 homes for 1 month takes 1 hour. Right? It's a highly parallelized system. So not before was this possible to investigate the simultaneous treatment of all of the loads on the residential feeder and the feeder behavior itself at the same time. Okay. How do we, okay, one word about control. It is a distributed MPC system. Each home gets an MPC controller. And what I want you to imagine is that a utility, or let's say a utility, brings on the door of your house and says, here, put this on your wall. And you go on your wall and you have Velcro, stick it to the wall, it's your new third step. It doesn't say Nest on it, but it says Grid MPC, right? So it's a little $50 device for 50 euros to stick it to the wall, and it does the MPC. So what you see here has been designed with the intent to make it implementable in relatively cheap hardware. We didn't want to have to require people to run a black large PC in their basement, but something that they could actually afford and something that is lightweight. So the models have to be very lightweight. Okay. We're manipulating temperature set points, and we're manipulating half-hour time steps. So for 1 day, we're making decisions on 48 half-hour temperature values, and we are looking at 24 hours. We're coming up with the best strategy for the 24 hours, and in a normal model predictive control, you would take this strategy and you would execute the first step, and then you would make another prediction over 24 hours, come up with a new strategy, and implement again the next step. We don't have to do that. What we do is we predict, optimize, come up with a strategy, and then actually go the full 24 hours. Why can we do this? The answer is not on your cell phones. Why can we do this? Why can we go 24 hours at a time? Because of the right. So what is uncertain in this? What do we not know? Is there, I mean, am I exposed to any stochastic effects? Any things that I don't know that change? Right, normally, yes. Normally the weather would change, right? I make a prediction, I do something, and then the weather forecast changes saying it's going to be even hotter than you thought it would be, or it's going to be a little colder. That's not the case here. The reason it's not the case is because we are in a certainty equivalent world, and we are looking at the maximum possible potential when the weather is known and the building behavior is perfectly known, right? This is perfect knowledge, okay? So that's why we can go forward in 48-hour steps. We're using an optimization system called particle swarm optimization. That's very popular, and we've modified it to include a number of neighborhoods, and it works very well. We've recently, for most of my optimization work, have gone more towards multi-objective optimization. We're going away from particle swarm to multi-objective optimization, but this is what we've used here. Okay, so how does the overall process work? We read in the simulation and weather files, we create a unique controller model for each of the homes, and could be thousands of those. For each building, we execute the following steps. We generate a candidate decision vector, which means we're going to try something out. Then we simulate the planning horizon, check how good the solution is, and iterate steps 1 through 3 until we find the best solution. We then write the PowerFlow input files, and we initiate the GridLab B PowerFlow simulation. And all this is happening for as many days as we're analyzing. So now we've got this, if I may call it proudly, this big Swiss Army knife, right, with lots of blades and screwdrivers and all these things. Now let's put it to work, right? So what is the Swiss Army knife? Just so you understand. It's a system built in Java that can optimize any feeder model you want. It doesn't have to be in the United States. And it assumes that all of the connected residential load, or a fraction of that connected load, is potentially flexible, right, and somehow react. That's where we are. Okay. So the first study or use of this system I would like to show you is demand response, DR. DR is very popular in the United States to help us with capacity limitation on our power system. And DR normally, maybe I say it here, whoops. So in demand response, what we're trying to do is we're trying to cut the top 2 to 3% of the hours in the load duration curve, right? You all know what a load duration curve is. Please understand. Load duration curve. Over the counter, you left one? No? It's sorted, right? What is that example? Duration curve. Okay, so did everyone hear Professor? Okay, good. Just so we know what we're talking about. And typically it's just a few days out of the year, right? So it's the hottest years most likely, and but it's not necessarily. And it typically involves also programmable communicating thermostats that are installed. And when you accept, or when you participate in a DR program, you accept, like Endesa rings at the doorbell and says, here temperature set point a few times a year. And if you put this on your wall, we're going to reduce your utility bill by 30%. Would you participate? That's kind of the idea. And they come up with different incentives, but the idea is just a few times during the year we're going to make you uncomfortable. Okay? And it's voluntary, and you can opt out. Opting out is an issue that needs to be considered. Okay. Fine. So it's the worst case scenario, as you hopefully will see in a second. I'm using this benchmark for comparison, and it does represent the maximum allowable or achievable, not allowable, but achievable demand reduction. We're going to look at a number of cases for this. We're going to look at 2 participation levels. One is 70% and one is 30%. So here's a little bit of arithmetic for all of you. 2,146 homes, if 70% participate, how many homes are participating? Approximately. Something like that, right? So it's 1,400. Thank you. So it's a lot of homes, and at 30%, yeah, it's about 600-700 homes, right? So just to keep this in mind. And the duration are 2 hours or 6 hours in duration. And it's we're going to look at the day that is the peak day for the distribution feeder. And how does it work? And that's very common. When the event occurs, your thermostat, wherever it is, let's say you like the temperature at 23 degrees and you like it at 25 degrees, it doesn't matter. They're going to add 2 Kelvin upward. We're just going to raise the temperature by 2 Kelvin. Okay? So this is what happens in Houston in a 2-hour event. So this, remember Houston was the 12 megawatt feeder. This is about 12 megawatts. This is what's happening at the feeder level. What do you see? Rows in the back. What do you see from the back? Maybe you don't see. You see it. And volunteers in pink shirts, for example. Pink concept. So, if there's any doubt, it's this red line is doing nothing. That's the standard, and then the demand response is this line. What is happening on the feeder? In the demand response case, where 70% of all the homes in Houston on that feeder, in Houston, or more feeders, participate in the event. What do you see?
With increasing power and then a peak that is terrible.
It's pretty terrible. Yeah. So both observations are good. The first one is, if the goal was to achieve a one-time really big demand reduction from 10, 11 down to 7, right? 4 megawatts of load being shed. Yeah, that looks pretty good. But how long? Right? Not very long. And before we get to this effect here, can you tell me what's happening here and why? At this point, you might be thinking, can you not just talk? Why is he asking so many questions? But maybe it's hot outside. You don't want to go anywhere. So what is happening here?
Well, the temperature, I think, is becoming hot, and then all the machines starts working in order to maintain them at the reference temperature.
And do you think that, remember that the systems in the homes are compressors that turn on or off, right? 1 stage, 2 stage. So they're not continuous modulating systems. Do you think that all systems turn on at the same time?
They are static.
All of them?
Not all this at the same time.
Why not?
Because of the constant, the time constant of the house.
You have 4 megawatts.
So my interest is in this. What is this here? This is 3 p.m. and this is 1 hour, right? In this 1 hour we go from 7 up back to 9 or so, right? We're adding 2 megawatts. Not all of them, but so why do we see this curve here? We see it because there's something I can tell you. The homes are all different. They're not all the same, right? It's not just one house cookie cutter. We spent a lot of time in looking at databases on characteristics of homes. So they're all different size. They have different orientation. They have different amounts of windows. They have different amounts of occupancy, different thermostat set points. And we look and we try to distribute or set up parameter probability distribution functions that characterize the actual building pool in Houston, different from New York, and different from Los Angeles. And when we say 70% of the homes participate, that means randomly we pick 70% of those homes. And every time we pick 70% of the homes, they're different homes that are actually in the pool, which is exactly what happens in a real demand response event. You don't know who participates. Remember I told you they're often voluntary, so if you don't like it, you can say, no, I don't want to. A typical scenario would be, Professor Antonio has a party, and he gets the call from Endesa saying, I'm sorry, but you're going to have very unhappy guests, and he can say, no, I'm opting out. I decide not to participate because it's an important party. So that is what many times happens. Now, I tell you that this is 70%, and what I also haven't told you is that it's actually for 50 different samples of 70%, which means what you see here in green is actually a distribution of responses. And it looks like one response, right? Do you agree, right? So even if I tell you that 50 times I'm selecting 70%, about 1,400 homes separately, but it ends up being so narrow, the reason is because when you pick 70%, you're picking the majority of the homes, so you're picking the same homes over and over again. And so the buildings have different characteristics, and so which building is, or which class of homes is responsible for this increase here?
The ones that have the less time constant.
Less inertia.
And less the lower time constant. And so can maybe some of the students tell me what types of buildings are those? If you have a pool of modern, fancy, highly insulated, triple pane window versus the old and inferior, no insulation, single pane windows, which ones are the old ones, right? The old ones will start causing that increase in demand. Okay, good. Right. Yeah. So okay, so we haven't, this is, here's an American idiom I want you to learn tonight. This is what we call the 800-pound gorilla in the room. Yes. What's the 800-pound gorilla in the room? It's this big animal in the room that no one wants to talk about, right? But it's really very present, right? So what is the 800-pound gorilla in the room? Ladies. No, it's pretty heated. More heated, but what do you think? So it's a 2-hour event. We start at 3 o'clock in the afternoon. At 5 o'clock things are over, and then does the problem of supplying power to buildings end at 5 p.m.? No, it doesn't end, right? Because at 5 p.m. you still have a little bit of reduction here, right? You see this reduction? And then what happens at 5? It's actually automatic. They don't have to come and go. Remember what your set point is automatically reduced, right? Because that's the rule. They tell you for 2 hours you're going to play with your thermostat, it's setting it up, and then they're setting it down again. And this is called a rebound. Right? It's a pretty problematic effect. And how could you deal with this rebound? So you, for example, you are not sending all 1,500 homes to set point, or the set point reestablishment at the same time, but you stagger it every 5 minutes, right, or every 10 minutes. So you could avoid some of this. But this is a common problem in demand response programs, which is, yes, we want to help the utility in times of grid stress, and we do, right? There's a little bit of help here, but this looks like a big problem, right? To all of us. Okay, and if we now do this in Los Angeles for 6 hours and 70% participation, now we're basically saying as of 11 o'clock to 5 o'clock, 11 a.m. to 5 o'clock, but we're in Los Angeles.
It's different because not all the people from Los Angeles has air conditioner.
That's right. That's right.
Less buildings are participating in this regulation.
Right. So you're correct. 70% of the homes, not fewer of those have air conditioning, but it wasn't all that much fewer, right? Do you remember the numbers?
Yeah.
Lots of numbers. Was it half in Los Angeles? In the 50s, right? 50s. So that, yeah. So you're right. A lot of the set points are adjusted in homes that don't have an air conditioning system that would have an electric change, or that would cause an electric change. But what do you think is happening here? This looks like a smaller relative change than in Houston. Does it to you? And why? Because we're not in Houston, right? And what's different?
The temperature doesn't change as much.
So in Los Angeles, it basically just doesn't get quite as hot, and so the fraction of energy used for cooling isn't high, right? And so when you ask 70% of the homes, of which only 50% have air conditioning, to shed their, to reset their set point. Other loads dominate that problem. You know, some commercial loads and TVs, and I don't know what it is, but it's not necessarily air conditioning to that degree. And I hope you can see that at this point you're losing most of the effect after 1 hour or 2 hours, and then you have a residual effect, you have a rebound. Go. Okay, so let's just focus on Houston for 70% of the homes participating. Peak demand, yes, we can reduce. I said 4 megawatts early. This is 3.7 reduction. That's good. 3.7 megawatts reduction. But the rebound is higher, right? Plus 4 megawatts of rebound. The average demand has been depressed by 1.65 megawatt. So this is good, but it's of course much less than the initial, and the rebound is significant. Okay, so let's see where we are. Demand response has large peak reductions, but the reductions are not sustained. It's a matter of time until we get back. The rebound can be as larger than the original reduction. We've seen that, and we can improve the situation. This was an extreme example. We can use staging, as I mentioned. We can ramp the set point down instead of saying, now take it down from 2 Kelvin above your set point down to your set point immediately. You can stage it down, and that might help. But it's not good. So this will serve as our benchmark. Okay, now, by the way, have we done any optimization so far? Have we done any MPC? Scratch. Have we? No, right? This is another slang term. This is the state of the shelf. You know the term state of the art? State of the shelf means you go into the store, you pick it off the shelf. It's what we do today. So, state of the shelf. It doesn't need any optimization. Now we're actually going to use our Swiss Army knife. Okay, demand limiting. So it's meant to be a very simple alternative to demand response. It's completely distributed. And the idea is minimize your demand without creating a rebound. And we're hoping that the individual optimizations yield an aggregate demand reduction. We're going to use our DMPC scheme to minimize demand at each home. Again, look at 70 and 30% of the homes. So, oops, there is an equation. So here we're trying to minimize the maximum moving average of the demand in a particular time window. And so this is the moving average, not too bad. One of the things I want to point out is that for this analysis, during occupied times, we're allowing the occupied lower bound to be 2 Kelvin below the set point, but not above the normal set point. So during occupied times, we're allowing to pre-cool a little bit, and during unoccupied times, we're allowing the temperature set point to be raised to +3 and lowered -5. Okay. So now let's look at Houston, and let's look at the month of July, and you see the first 15 days of the month of July. And I would like you to remember that the red curve is the unaltered demand curve without doing any of what we've been discussing, and the green aqua-colored curve is what you get by applying our strategy. In this case, we're looking at Houston. We're going to look at 70% participation, and we're looking at 15 days in July. And I would like to point to a few things. This day and this day, I hope you can see that we have clipped this peak and we have filled this valley, right? And I take a particular day here. This is the 2nd of July. This is this day, a little bigger. And I hope you can see that we've shifted the loads a little bit here into the night hours. We've clipped this peak. We've reduced ramping here, so this is less ramping here. So it looks like a good thing. And I think now you can actually see the sampling. You see this dark green line in the wider band here. This is always happening by picking 50 times 70% of all the homes, right? And this is to show you the range of variation from the sampling process. Okay, so demand limiting. and we're going to, again, because there's lots of numbers, we're going just to look at this one. At 70% participation, we're increasing energy consumption by doing that by 3.8 megawatt hours. We're using more energy, okay? We're reducing peak demand by 0.6 megawatts. The peak to valley ratio, that ratio is set as 100% under base case operation. And if we achieve 81% of that, that means we've improved the peak to valley ratio by 19%. Does that make sense? So if the peak is 12 megawatts, the valley is 6 megawatts, the peak to valley ratio is 2, right? 12 to 6. And that's 100%. And if you reduce that by 20%, it would reduce your peak to valley ratio to 1.6, from 2 to 1.6. That's what this number means. Load factor is you know what load factor is, right? No, electrical power systems engineers. Load factor? Okay, load factor is the ratio of the average load divided by the peak load. Okay? And that load factor has been improved by 5.5%. Ramping is, what's ramping? Ramping is the sum of all the load changes over the course of the day, right? So you basically add up how much variation there is on your load profile. And this has been reduced. So all these are good things except for the increase in consumption. This, let me just skip. So, it's very interesting, but we're taking a look. So, improvements across the board for most metrics. No, I was lying, not intentionally, but I'm going to look at it. So this is looking at storage efficiency of my building as a storage device, and 100% is maximum. And this is basically looking at a particular scenario for Los Angeles, and we are looking at the month of July and the cooling set point at the upper boundary, and we have a wide range of homes. Some are more efficient and some are less efficient, and the less efficient ones basically are down here. The more efficient ones are back here. So the question is, if I pre-cool a building, how much do I get back later on? And in older homes, I'm more here. In modern homes, I'm here. And we don't know right now why this distribution is bimodal. We don't know. But it's an interesting analysis. We did see, and I hope you all agree, that there was peak shading and trough filling, both of those. So this is a trough, right? We filled this trough, and we shade this peak. Okay. We saw no rebound as we had hoped. Okay. The next one is day-ahead pricing. So the idea is, if I'm going to use so we're going to use price as a proxy for demand. And we're going to expect that the homes change their operation in anticipation of high prices. So you're using the day-ahead pricing for tomorrow as a signal for the optimization of the homes. And so think of it this way. There's a price signal sent to thousands of homes. They get this price signal for tomorrow. They then develop a strategy, and without feedback mechanism, they're going to implement that. And this is what we get. We developed a model for the pricing as a function of temperature and temperature difference between the hottest and the coldest time of the day, hour of the day, day of the week, and if it's a weekday or weekend. And the model is actually pretty good. You can see the agreement here for a case of California pricing signals in 2013. So this is a case where each home is charged with minimize your operating costs for the next day. And what each home is trying to do is pursue a breathing strategy. know greedy is? So if you want all the money in your pocket, that's greedy, right? And so you don't care about what happens to the left or right of you. You optimize to make and take advantage of the low prices at night and high prices during the day. Okay? And the prices are hourly. So we have a price profile that's not smooth, but it's actually stepwise hourly. And that leads to steps changes in the demand curves. And we'll discuss this in a second. And we also have the problem that the hourly price changes kind of lead to a synchronization of the controller. Because remember, the controller has 48 half-hourly decisions to make in each home, right? And at the end of every hour, price is changing. If you have a change from a low to a high price, you will see some planning for that. And you can see this in these results. You can see these unintended consequences. This looks good, right? Here, July 2, but you see this big peak here. We didn't want that. We didn't want that. We didn't want that. The rest looks good, right? So taking the price for tomorrow seems to lead to these unintended consequences. Now, if I set the upper degree or the upper boundary to be not plus 3 Kelvin in the case of the unoccupied time period, but actually 0, that's the 0 degree problem, then we eliminate some of these problems, but we reduce the savings, so it's not as good. And then if we next make the price smooth, instead of hourly set points, actually has a smooth profile, we improve things further, but I would like you to notice that we have some very strange effects, right? We wanted to clip this demand, this peak here, and what we get is this spike in here. We still get this spike in here, so not really what we were hoping for. We actually get a reduction of overall electricity consumption in this default case, but that's because we changed the set points a little bit. When peak demand is increased, not what we wanted, peak to valley ratio is reduced by 7%, that's good. Load factor has been reduced, it's not what we wanted, and ramping has been increased. So all things we don't like. So what we did then is this is an interesting analysis. This was the base signal to the optimization, and we take that and give it to each of the buildings. The total of all the demands is then added and leads to this profile. Then we take that profile and ask all of the homes once again to optimize, and we get this profile. And we repeat this, and I hope you appreciate that what happens is as you take, we begin with a price forecast, and we get an aggregate demand from it. We use that to optimize again and so forth. What you see is we introduce these interesting oscillations. So we are noticing that using tomorrow's price, real-time pricing, is not necessarily a good idea. It may not be the best signal. We get some improvements, some are not. We definitely have more variability in the feeder demand. We have new peak demand. It's not entirely predictable. I don't like it. The objective function is greedy, right? It tries to minimize each home, the operating cost of each home and nothing else. And so that's not necessarily aligned with the global objective, which was to smooth electricity demand, right? So each home is just thinking about itself. So now we're using the system in a new way. We're using it for directed optimization. And this is what I call load shaping. And in load shaping, we're taking the following steps. We are generating a reference demand curve that represents what you want the feeder demand to look like. It's the desired feeder demand. You take that feeder reference demand curve and turn it into a reference demand curve for each of the homes. It's a translation. And then you try to minimize the difference between the house demand and the house reference demand. And that's a lot of words. I'll show you a picture. So if this is the feeder demand, and this is our Los Angeles feeder, and that's shown in red here, I don't like this. There's lots of ramping, and there's this lunchtime carve out here. I don't like this. I would like to have this green profile. That's much smoother, right? Much easier to follow. And so what that does, it basically means during these times, I want to increase my consumption. And during these times, when the red is above the green, I want to reduce my consumption. Yeah, you see that? So this is my desired profile. There are times when I want to consume more, and there are times when I want to consume less. And you can see with this being 0, the reference signal looks like this. Consume more, consume less, consume more, consume less. And the question is, if all homes do this, will the final feeder demand profile look like the green line or not? That's the question. So if I give all of the homes a reference feeder profile, I generate this signal for each of the homes, because I know if I didn't do anything, I know my reference house demand, I know my desired reference or my desired demand, and I basically can generate that signal. And so the optimization is about minimizing the deviation, right? Minimizing the sum of the deviations between those two. And each home is trying to do that.
Load forecasting.
Pardon me?
You must have load forecasting.
Yeah, load forecasting is implicit because I have my model.
You need to predict the forecasting.
Oh, the feeder, yes, I need that forecast. Yes, that's true. Yeah,
There's uncertainty also.
there is some uncertainty in that. Okay, that's a good point. And now these are some of the results, and I'd like you to just get a sense for what happens here, right? Things seem to improve here. There's smoothing here. I seem to be filling here, and I seem to be filling here. I think I have one day that I picked out. This is July 7th, this day here. And you can see that for 70% in Houston, we can definitely see an improved profile. I hope you can agree with that. Okay, and we consume more, we reduce our peak demand, which is not necessarily what we asked the system to do, right? We asked the system to follow a peak profile. Peak to value ratio is improved by 16%, load factor is improved by 3%, and ramping has been reduced, which is all good. These are all good things. Again, more energy consumption is not a good thing that we have to discuss. So, in summary, this new load shaping methodology, it does shape peaks, it fills in troughs as we expected, it improves all metrics except for consumption. The demand reduction is modest, but that's not really what we asked it to do, right? We didn't say reduce demand, we said follow a profile, okay? And it's more effective in Houston where there's more of a flexible cooling demand. It's limited by the storage efficiency of our homes. We are dealing with what types of homes in the United States, for the most part? What kind of construction is this? Yes, but what's the construction material? Yeah, it's wood, it's timber frame construction. It's historically paint on the outside. It makes a lot of sense in hot climates. And yeah, that's just not, unfortunately, for cost reasons and others, not quite the case. And definitely we see a more controlled and predictable response than in the price-based optimization. I didn't like that at all. So let's add some solar to this. Now the question is, can variability introduced by rooftop solar be removed through this load shaping methodology? So we're going to add solar model to each of the buildings. We're going to distribute solar to the homes according to predefined penetration levels, and I will not spend too much time on that. And then we'll apply the load shaping methodology, again, using the feeder demand with the solar contribution as a reference. Okay, so there's a solar model. This is an efficiency, temperature dependency of a photovoltaic cell. These are the inverter efficient. This is, excuse me, the DC direct current power, and this is the AC power with the inverter efficiency. And In the United States, there have been quite a few incentive programs for people to add PV on their roofs, and they typically were told, we want your PV system to cover no more than 80 or 100% of your power. What they don't want you to do is put photovoltaics on all of your available surfaces and overproduce by much. So 80% is a pretty common value. In my state, it was 100% in Colorado. Okay, PV watts, pretty common model. What we've done here behaves very well, and I think you agree that it's validated. In the interest of time, now we're adding on a lot of the homes, we're adding, this is the high solar penetration phase, so we are in Houston, we have 70% of the homes participating, and the high fraction of homes have PV on their roof. And I think you can definitely start to see some of these carve-outs due to the duct effect, right? You can see a lot of sun here and here. And I'll pick, oops, no, I don't pick one there. I point to this July 7th. You can see how this trough has been filled and this peak has been cut. So it seems as if this method is improving things a little bit. Because you're all electrical engineers, we then took these profiles and we analyzed them from a spectral analysis perspective. And what we did is we basically conducted a discrete Fourier transform on the on the feeder demands for the two cases. And we asked ourselves, what is happening in this optimized case when we basically ask these homes to achieve a smooth feeder demand in the presence of the solar system on their roof. And I want you to look at this frequency bin. These are the low frequencies. This is greater than 24 hours. So that's basically the DC portion of the spectrum, the long wavelength portion of the spectrum. And what you see here is that when we optimize, we have a greater content in terms of spectral power in the low frequency components of the signal, which means we have smoothened out the signal. There's less high frequency components. That's all this means. Right? So this is lower here, this is about the same, but this is significantly lower, but this is higher, which is good. We wanted to smooth out the profile. Yeah, this is just another case, July 1st. We can see, this is what we would see with solar everywhere. This is obviously, clouds moving away and then having quite an amount, a significant overproduction, or I'm not sure if this is clouds. No. But we have some trough filling here and we have a smoother profile. Good. But we have limitations. So this is Los Angeles with less of a load. It's a very sunny climate. And you can see the duct curve really building here. You look at July 12th, right? You can see the morning and then the PV carving out. What can you notice here? I know you've been seeing a lot today, but if you keep engaged and maybe tell me if you see July 12th. Or 13th. Pick your day. If you look at the red curve, which is the feeder demand with PV on the homes. So this should remind you a little more of that duct curve I showed in the beginning, right? Does it? Right? So the afternoon ramping, the evening ramping, the morning downward ramp. And what do you see? What you see is that I cannot really fill this, right? There's limitation. And remember, this is in Los Angeles. In Los Angeles, I have fewer homes that have air conditioning, and then it's a smaller fraction of the overall load. So I can do a little bit here and here, and I can clip a few things, but I can't, here you can see a nice effect here on July 2nd, but I can't completely smooth out this profile, right? I cannot fill all of this by massaging my cooling load profile. Okay, let me just come to the summary of rooftop solar. We can absorb some of the variability introduced by rooftop solar. We reduce a lot of the secondary peaks that happen later in the day. We can lessen the ramping, but we cannot prevent ramping from happening, right? We saw some of it. And sneeze. So these are good things, but we have an increased consumption of about 5%. And we seem to be able to provide short-term shifting on the order of a few hours more than long-term shifting. And that's simply by virtue of the fact that the homes are lightweight, right? If you pre-cool a building to -5 Kelvin from the set point for a number of hours, and then basically let go, this stored energy doesn't help you through a day's worth of operation, but a few hours. That's why we see this. Now, last thing, and then we're ready to wrap it up. Utility scale wind. Now, we are looking at wind produced at the utility scale. It's not every home has a little wind turbine, but it's actually it's provided outside the feeder at higher voltage levels. And the wind that we have will introduce variability to the supply, and if we have high penetration, we might have curtailment and additional ramping. So we will model wind outside the distribution feeder. We will inject the wind production into the feeder to create a composite feeder demand after demand. It's kind of like a net feeder demand after wind. And we're going to apply the load shaping methodology. Okay, that's the last analysis I'll present to you. Okay, this shows the behavior of two types of wind turbines. We use a General Electric and a Vestas model, and we scale things up. And the approach we used is we ran each of these two models, wind turbine models, for 1 year for each. Each of those wind turbines was normalized its output to 1 megawatt hour. We then mixed them 50% from each turbine type, and then we scaled them up by certain factors. So, for example, in Houston, we used a scaling factor of 10,600 in order to achieve 25% of wind penetration. And that's these two numbers, 25 and 9.4%. These are not numbers that we came up by pulling them out of our sleeves. Those are actually numbers that the National Renewable Energy Laboratory is suggesting as two scenarios. It's the high penetration scenario and the low penetration scenario. And so we said, well, if that is happening, what will this do to our feeder demands? So, and I think you can see here on some of the later July days a lot of the wind activity, right? You can see the wind cutting out here, or excuse me, cutting in, right? Is it cutting out or cutting in if I look at this day? In, right? Because the net demand goes down, right? So wind production went up. Your wind production went up, and it came down, wind production up. You can see quite a bit of this variability here. And so to the extent that that is predictable, the question is, can we utilize our building thermal mass as a way to improve our profile? And let me just pick July 7th. What do you think? Some positive effects, right? I would say, we definitely filled this trough here. We put this peak. This underproduction, the wind must have stopped here. We have, this is the same spectral analysis. Just look here, the low frequency signal content has increased again. So we have smoothed out the demand in terms of its frequency content. We see peak demand reductions. We see great improvements in peak to valley ratio, load factor improved, and ramping reduced, but increase in energy, same as we saw before. So load shaping method appears to address some of the needs. If we have power produced outside the feeder, we have the ability to remove a significant amount of variability. We see benefits at all levels of building participation and penetration. We see a reduction in peak demand, but we see similar limitations, right? There's still timber frame homes. I can, as much as I have perfect knowledge that there will be a certain wind profile tomorrow and that the wind will suddenly stop for 2 hours and then pick up again. If I know that perfectly, my homes are still made of wood, right? They have limited capacity. Okay, so with this I'd like to come to the conclusions of my talk today. We saw in the demand limiting case, relative to demand response, we saw significant demand reductions. We saw no rebound effect. Using day-ahead pricing, this is what I call dynamic pricing. I didn't like this, so designing these controllers to be price responsive must be very carefully done. And we've seen a lot of additional variability. So taking this thermostat and just giving it the day-ahead forecast for electricity price as a signal to optimize amount is not a good idea. Looking at load shaping, we see that load shaping, the reference curve idea, is very effective at removing variability. We see some demand reductions. We see a reduction in variability of solar on the feeder, and we also see the ability to absorb some variability when we introduce wind outside the feeder. Residential HVAC, heating, ventilating, and air conditioning MPC is definitely most effective in terms of short-term variations, just a few hours. We cannot shift demand for long time periods. The method I've introduced today can be applied to other loads, such as pool pumps or electric vehicles or dishwashers or whatever you can think of. So it's available to do that too. The distributed but direct MPC method can be implemented. So the computational requirements to do this on a small embedded PC, a small thumbstick Linux system, or in the United States we use a lot of Arduino and Raspberry Pi systems. Maybe these are names that you've all heard of in your labs. It can be done that. There are limitations, and with this I'd like to finish, of how much of the cooling demand is flexible. Less in Los Angeles than in Houston, right? And if you want to achieve, or think San Francisco, there's no cooling whatsoever. So if there's no cooling, we can't do anything. Storage efficiency of wooden homes, timber frame construction. We haven't looked at forecasting uncertainty. I mentioned to you that the forecasting is perfect. And model accuracy. So far I assume the models will be perfect. But if you do this in real time, you would have to have a model in your thermostat. And that is identified in real time and included in real time. So we want to take this into the future. We're looking at short-term curtailment and ancillary services. We're looking at uncertainty in weather and forecast. And the second to last point is very important to me. I've shown to you several times today that we're increasing the total feeder level energy consumption to achieve feeder level benefits like improve load factor and reduce ramping. But what does it mean in terms of primary energy? That we don't know yet. And so right now we're actually looking at the analysis of the carbon emissions impact and the primary energy impacts, not at the feeder level, but all the way back to the primary energy source. Yeah, and this is it. Thank you very much for all of your attention tonight. I know it's been long, but not too long. Thank you, all of you, for your attention. And I know you have burning questions. Right? At least one. Good! Oh, we have to do this.
Actually, when I raised my hand, I was asking a question, but then I will not. You first. No. Okay.
Have you think about use your model for on little shops, for example? The model for little shops, for example, the model you have shown, it's only for residential loads, but in one feeder you have the residential loads, little shops. Have you think about use your model to little shop to have a better model or forecast?
Good question. So the question was, have we considered applying the same model to shops? There are lots of shops. So the short answer is no, we haven't, but the good part is shops behave quite similarly. Most shops in the United States have the similar air conditioning systems, direct expansion systems. They have different set point profiles, just the opposite of what you see for your homes, right? They're low during the shopping times and high when people are home, right? Just inverted. But that's simple. The system we developed would allow us to easily define the resistances and capacitances and the windows and all that of shops. So we haven't done it, but we could include that. Right now, if you look at the Houston feeder, I think we had a total of 2146 homes, but we had some commercial loads on there too. We could include a number of those at the same time. I think we would not make, there wouldn't be many errors in oversimplification, because a lot of shops do behave like single zone, have a single zone behavior. So, and I think we could do that. And there are lots of shops where we could apply that. The dilemma in shops is that, at least in the United States, I think the idea of asking shop owners, I'm thinking, what's your favorite shop here? What's your favorite shop in the city?
I don't know. A restaurant or a bar?
Now your restaurant, but you asked me about shops.
Shops, I don't know. Game shop.
Game shop, good. So if the idea is you own a game shop, and then and you have customers coming in that hopefully spend a lot of money, and then you make them uncomfortable while they're about to shop, right? That's the dilemma, right? How can you help the utility with their grid problem, but that's not really my problem. I'd like to sell my games to you, so I'd like to not have anyone touch my thermostat. So that's just an implementation hurdle I want you to think about. Okay, let me take that microphone. Any other takers? He's my saving grace here tonight. And you can all think about another one.
Have you think about use your model for water heating? Or, for example, in Spain, a lot of houses use electricity to heat the water. It's almost the same to heat water or cold water that air.
Yeah.
Have you think about use?
We call this domestic hot water heating. Domestic hot water heating is something that we could easily add, as it would be a European context. We haven't, in part because the hot water in the United States is commonly prepared using using gas. It's a gas water heater, and so we didn't look at that. But it would be an easy thing for us to add a model for domestic hot water with a tank and a stirred tank model of that. That would be possible. Okay, I know you had a question.
Yeah, my comment was regarding the last set of experiments with wind energy. Can you go back to the curves? I mean, regarding basically the extremely difficulty to predict, for instance, these gaps early in the morning, it's very unlikely that you can predict the day before with enough certainty the wind production at local level. I mean, for instance, you're talking about the national production in Spain, the uncertainty is not bad. But if you are geographically in a local area to predict the wind forecast, is very uncertain. So it's very unlikely that you can forecast so nicely. It's okay, but it's not very realistic, according to our experience in wind forecasting.
I grant you that. I do think that there's a lot of work in improving load forecasting models, regional load forecasting models, and if we assume that those improve over time, maybe we get a little more of that ability. But right now, with perfect forecasting and perfect model accuracy, we are somewhat optimistic. I agree. Yeah. When it comes to the wind, these effects. But the other thing to remember is this is, can we pick a date here, Antonio? Maybe this is July 4th,
Yeah.
right? So we have wind cutting in, cutting out, and all that. So if this is a fast enough MPC process, I can actually, to the extent it's predictable, to the extent I can predict these changes here more than I can predict the changes later in the day, I can adjust my strategy by repeating the optimization and actually doing the true MPC, which is predict, execute one time step, and then next time step predict again. So every half hour making the forecast.
Yeah, the prediction is deteriorating with the time. I mean, the first 2 or 3 hours is relatively good, but 24 hours is...
So as I'm getting, these are the early morning hours, as I'm noticing, as I have improved information about that, again, you are correct that I need good forecasting models, but if I can assume that I have good forecasting models for regional wind, I might actually capture some of that benefit here. And it's the first few hours that are the best quality in forecast.
Yeah, I think that in the medium term, these techniques can be more profitable in the presence of electric vehicles because they will be more versatile, more flexible to control. The charging of vehicle will be more flexible, for sure.
Yeah. When it comes to electric vehicle, my question back to you, and maybe here in the audience, is there's quite a debate in the United States about if you own an electric vehicle, to what degree would you allow the utility to manipulate your state of charge, right? Because if, for example, you have a new Tesla in your garage and you feel like going for a test drive in the middle of the night, and the utility decided to use your car battery as a storage for the grid, you might be really upset, right? And then there is, I read at least about quite a few electric vehicle manufacturers that say, if we give control to the utility, a vehicle to grid idea, we are impacting the battery life, right? We're impacting the cycles that a battery goes through, and who's paying for that? If you have a battery being discharged twice as often as you would normally, right? Your normal process, you drive to work, you plug it in, it charges, you drive home, and you recharge the rest. But if we have this very aggressive charge discharge,
Yeah, even with a single daily cycle, daily charging cycle, you can stop charging and continue charging later.
right? I agree.
No charging and recharging.
But just charging, control the timing.
Yes, I agree. Yeah, I'm in agreement that if we had a good fleet of electric vehicles available, it would be easier. And this, again, was research. We didn't know how much, what the potential of the system is, and we noticed that actually when it comes to wind variability, the system is very good because it's the shorter 2 to 3, 4 hours that the thermal mass is available. If we have long time periods, 8, 10 hours that we want to ship loads away from, that's difficult using buildings. So we actually think that these are, promising results, but the statement that Professor Antonio made is correct, right? If I don't have perfect knowledge of wind cutting in and out, then I don't see that benefit. Good.
More questions? Even in Spanish, if you are shy, he will understand Spanish. So he's taking many lessons, Spanish lessons, so no problem at all.
Complete waste of
Just
time.
speak slowly and make the question in Spanish.
Turn around. Don't be shy. Kathy. Sorry, I didn't mean to put you on the spot.
But it seems that there are no questions from our I think I have another one.
Saving grace. Yeah, please.
Have you think about, because you are doing this study, proving your model with a reference level, a reference curve. How do you make this reference curve? Because you can make a reference curve that is easier to achieve than others. How do you, I don't know, how you choose one or other or each half hour?
Right there.
Okay.
I understood your question.
Okay.
I'm embarrassed. I don't know. No, very good point. This is part of the research. What I showed to you was that the reference curve was much smoother, had less ramping, right? It was really like a beautiful walk in the countryside, right? That's what we want. But is there a better one? Is there an optimal one? And that's the next phase of the research is I really want to connect what you saw here, the buildings, the demand side, with the complete supply side, with the unit commitment and dispatch model, to actually ask ourselves, what would be the profile that would, for example, minimize carbon emissions, right? Or minimize the use of coal, or minimize the need for operating a particular type of power plant, right? So that's where we are right now. You caught us in the beginnings of the research where we say, we know that this isn't good, so let's come up with this and see if buildings can follow a smooth profile. But is that smooth profile good, or is this one better? We don't know. It's exactly where we are. And we hope to get better answers of what should, or how should this reference demand profile look in the near future. Thank you very much. Thanks to all of you for your good questions and your attention. And it's still hot and unpleasant outside. You didn't miss much. Thank you.
Final comment?
Yeah, please.
No, my final comment was also, my final observation was probably something to think about. Is the increase in energy is not so high, 5% or something. I mean, the total energy is, but this is not too bad, because actually what we are doing is storing energy. So it's a kind of thermal storage.
Yeah.
So to say, because we are not consuming energy the moment we need it. We are consuming earlier and relying on the thermal, So in some sense, this is storage. But if we were using chemical batteries, electrochemical batteries, the efficiency would be lower. So the increase in energy will be probably much higher. Not 5%, but 10%. So storing energy this way is more efficient than storing energy by batteries. So it's a good conclusion, probably.
Good.
Okay, thank you very much.